Hi everyone. So in this video we will see together a hands-on session on stitching. I will explain to you with the NanoFrazor how to do active field stitching or standard stitching. In the previous video you may have seen the presentation from Robin Erne, a colleague here at Heidelberg Instruments Nano. The presentation was given at the Thermal Probe Workshop, which is an event that we hold every year in our offices, where we have for 2 days a conference-like event where NanoFrazor users and people working with the NanoFrazor technology come here and give presentations about their research and their work. And we also have one initial day, which is a user meeting where we give presentation and we do sessions about more advanced concept for the users to improve your abilities with the NanoFrazor. So that was a presentation that he gave during that event, which I think was quite useful for you to understand how stitching works, the differences between active field stitching and standard stitching. Now we're gonna see these things with the NanoFrazor. So I just imported this design, which we can try to use for a stitching demo. You see this design fits in the range of the piezo scanner, so I can import it without splitting it. You see that I can also decide to change the dimension of the fields. But what if we are making this a little bit too large for the piezo scanner? Let's say we have to double it. So as you see here, now we have to split it in two fields. And you see here that we have a total patterning time here of 4 minutes. This is patterning time that is referred to the active field stitching. Maybe we can reduce it on Y to make it a little bit faster. It doesn't change much. Let's put it back to 2 because it's not looking so great. So let's try to do first a standard stitching. For standard stitching, we have a lower resolution but a faster process, so we will pattern this field, then we will move with the coarse positioning system here, and then we will pattern this field. While on the other hand, with the active field stitching, we will pattern this field, then we will read this region, and then we will align and pattern this other field here. So with the standard stitching, it's important to define an overlap that's large enough to accommodate for the error of the movement of the coarse positioning system. So I would say 0.5 and 0.2 should be okay if we want to be sure we can increase a little bit. Sorry, here I was changing the margin. I meant the overlap. So if we want to increase a little bit the overlap to make 100% sure that we are going to overlap the fields, we can increase it to 0.5 and 0.5. And you see that now this area basically is overlapped by 0.5 micron. This should be more than enough. Once we like this, we can import it and put in our warm-up. You see now the time is 2 minutes 52 because this time is referred to the active field stitching. If we want to use active field stitching, well, we have to select here active field stitching. So now we can start it and see basically how it works. And then we can also compare the standard stitching with active field stitching, maybe by reading the margin or the overlap region of the two. And we should be able to see that with the active field stitching, we have a better overlap of this line. It's depending pretty much on your application when you decide to use or not to use the active field stitching, also as you may have seen in the presentation. So if you just need a continuous contact line, for example, you don't really need an active field stitching. You can have a big overlap region to make sure that your line is continuous, but maybe it's something that doesn't require such a high resolution. Here we see the patterning is not was not great. Here the feedback was oscillating a little bit. In the end, we don't care too much in this moment about the patterning quality. We just want to see the stitching. So I reduced a little bit the gain to avoid this sort of oscillation, or hopefully it's going to be a little bit better. What we see here, this part of the patterning is not great, but let's not worry about this at the moment. When we do stitching of the fields, we have to be careful about the fast scan correction, and because if we flatten on left and right, but for example here, maybe this area is not going to be at 0, or this line is not always going to be at 0, we can have some flattening artifacts. So I will maybe disable it, and another thing that we need to keep in mind is where is the reference margin, at the right or the left. We can also choose this for every field in the geometry, so it's something that you should be aware, because if we set the reference margin on the left or on the right, then we may have different readings, and in one case maybe one reading is generating some artifacts. So we can see here that we have this overlap between the fields. In this case, let's say we want to have just a continuous line, and here we have roughly 40, 30 nanometers, maybe 50 of alignment error, which is due to the fact that we are moving our coarse stage, and this introduces an error. So we can also see that in this overlap region, we have a deeper pattern where we have the overlap between this TSPL and this other TSPL. And of course, it's going to be a little bit deeper, as expected. So now we've seen the standard stitching. Let's try to see the active field stitching. Move this. Here, and maybe we can try to read afterwards this area. So here, basically, we are going to do the first pattern exactly the same way, but then we will read this area so that we can align better. And then, of course, before reading, we will move with a coarse positioning system, maybe let's say here, so that we have this second field completely in the range of the piezo scanner, and we will use the piezo scanner only. So we will, of course, take advantage of the much smaller error of motion that's associated to our piezo scanner component. Again, here, let's not focus too much on the quality. of the pattern. It's not our main worry at the moment. So what we expect to see is as soon as this field is done, then we will move with the piezo scanner, with the coarse positioning system, and then we will perform a reading. So here it's almost done. Bear a few more seconds, and then we will see the system doing the reading to have the best alignment. As also mentioned in the presentation, we expect a stitching accuracy of around 25 nanometers. That's within the specs of the tool that are always met after we install the NanoFrazor at your labs. So keep this in mind when designing your geometries and when thinking of applications for the NanoFrazor. Can you have better stitching accuracy? Yes, but it requires some expertise, and it's not always guaranteed that you can go beyond the specs of our tool. So here we see that we are finally doing the reading, right? So we have this area to a reading, and we can select also the margin of this specific area. So if we struggle to actually read this, or we're not reading everything, you can increase the read margin on X or Y. And you can, of course, also change the margin from here. So now we are doing the writing of the second field after we perform this alignment. And we should be able to see a better alignment between the two fields. So we already see that this matches well. One thing that we should consider is also that the patterning here is not looking too great. So we have a very large adhesion length. So we struggle to pattern a bit here, but we see in general a better alignment. If you want to test more accurately the difference in alignment, you can try to align lines in high resolution, which is usually what we do with our site acceptance test of your tools. So here we'll just measure this area with a reading, but if you have thinner lines, then you should really be able to see and appreciate the differences between active field stitching and regular stitching. So now we'll just perform a reading of these areas. And I also want to rotate by 90 degrees. So by rotating, I can choose the best reading direction, because it's better to read in this direction rather than this. And this is no different from an AFM, let's say. So along Y, we can have 10 pixels, only take 29 seconds, so it's going to be a fast reading. So the first stitching that we will be seeing in the scan is going to be the standard stitching. The second one is the active field stitching. You can see here definitely the patterning is not great. But the standard stitching, here we see some not perfect alignment here. It's mostly a matter of the dimension of the tip, that in this case is we accumulated some contaminations for sure. But we saw also in previous videos that we had quite a large adhesion length. So visually we can already appreciate the better alignment of these two lines. But again, if we want to have a most accurate evaluation, we can use also other kind of geometries. Here I just wanted to show you practically a difference between the two processes. Also because I'm not using a very good tip, in the geometries folder you can also find this overlay and the stitching file. So in this case, by using active field stitching, if you repeat the structure over and over, you should be able to appreciate better the stitching accuracy, because here we are dealing with thinner lines. So this is pretty much it for this video. I hope you're able to understand a little bit more how to use standard stitching and active field stitching with the NanoFrazor, and what this implies in terms of operational capabilities of the tool, but also practically what you have to do it to on the software to perform these two different stitching methods. And as mentioned earlier, there are some parameters that you can tweak, like the read margin, the overlaps in the geometry. In the training videos playlist, in the geometry section, there's also a video that explains how to import the geometries, and you should also have already seen some of explanations of this specific setting. So I hope this was not new. If it's new, go back and rewatch that video. I hope it's going to be helpful for you, and this video as well. So see you in the next videos, and thanks for watching.